Which is the actual physical mechanism that regulates the Earth's surface temperature. In order to understand this point, we need first to look at where the energy on Earth comes from. We have energy stocks, often stored underground in the form of chemical and internal energy of materials. Fossil energy sources are an example of stock. They are actually the result of the photosynthetic action and centuries of gradual accumulation and decomposition of organic matter at proper thermodynamic conditions. Internal energy from the core of the planet is continuously transferred to the surface in the form of heat and geothermal energy of hot fluids. Most importantly, an almost constant flux of energy comes from the Sun. There is also the gravitational action of other celestial bodies, but this contribution plays a minor role in the Earth's energy balance. If stocks of energy are limited resources, though they can be available in very large quantities, solar radiation is an almost unlimited resource as long as the Sun will shine. We have already discovered in the previous lecture that solar radiation is indeed the ultimate energy source for the Earth's biosphere, ruling many of its physical mechanisms. Let's have now a deeper look at how the Sun distributes its energy and the potential amount that is available on Earth. First thing, the Sun distributes its energy in every direction. The irradiance, that is the power per unit surface at the top of the Earth's atmosphere, is a quantity called solar constant. To fully understand the solar constant, we need first to describe how energy travels from the Sun to the Earth despite the almost 150 million kilometers separating them. The Sun emits a flow of radiant energy of about 383 yoctawatt in the surrounding space. The spectrum of its radiation can be approximated to that of a black body at about 5800 Kelvin. Only a small fraction of this huge flow reaches the Earth. Solar radiation interacts with the Earth system to establish a so-called radiative equilibrium condition that eventually determines the temperature on the Earth's surface. About 30% of the incoming flow is reflected back to the space. The atmosphere and the underlying surface absorb the remainder. This absorbed energy is then emitted because both the Earth's surface and atmosphere are at temperature above 0 Kelvin. The spectrum of this radiation is centered in the infrared band and can be described as the radiation of a black body at temperature lower than that of the Sun. The mean temperature of the atmosphere-lithosphere-hydrosphere system accomplishes the energy balance between the incoming solar energy and the outgoing infrared radiation. We will discover later on that the physics of the radiative energy balance between the Sun and the Earth is fundamental to understand the global warming forcing. Let's now calculate the average amount of the incoming solar energy on the Earth's surface. What happens is that the solar constant is reduced by a factor of 4 to account for the non-planar shape of the Earth's surface and the diurnal rotation on its axis. The maximum irradiance outside the atmosphere is therefore about 340 watt per square meter. About 30% of the total is reflected back to the space because of the Earth's albedo. Albedo is not uniform on the surface. For example, snow and ice have particularly high values compared to forest lands or oceans. We say the Earth is also an emitter. In figure, the Sun and Earth radiative spectra are shown. The logarithmic scale was chosen for the x-axis, which gives the radiation wavelength. Two different y-axes have been used instead for the magnitude of the radiation, being the solar contribution much more intense than the Earth's one. What is central to observe is that the radiation emitted from the Earth is shifted toward the infrared region that is characterized by long wavelengths. Let's now calculate which temperature of the Earth would be in the radiative equilibrium with the Sun and in the absence of atmospheric interference with both long wavelength and short wavelength radiation. This is a rather extreme case just to show later the role of atmosphere in absorbing radiation. The effect of planetary albedo is nonetheless taken into account. The radiative balance is rather simple. The short wavelength radiation from the Sun corrected for the planetary albedo is balanced by the long wavelength emission from the Earth. The resulting temperature is 255 Kelvin, that is equal to minus 18 degrees Celsius. This is actually the temperature of a refrigerator, good to store ice cream rather than vegetation and human beings. We will discover later in the next lecture how the atmosphere plays a crucial role in absorbing radiation, thus altering the radiative equilibrium between Earth and Sun. This effect is such to bring the average surface temperature on our planet to an acceptable level for life.